So we've been talking up to this point about light and mixing light to get these different colors. So you can see down here we've got the additive colors that I was talking about. So adding the red, green, and blue together to make white light, and then getting our primary additives like yellow, cyan, and magenta. So the thing is that we know if we mix the red, green, and blue paint, we get those horrible colors, right? Like we'll get a nasty brown color or something like that. So if we want to mix pigments together to get colors that will work for what we need to use the right pigments. Pigments, of course, as you probably know, are particles that absorb specific colors. So you probably know that pigments will absorb things, but we need this correct pigments to absorb specific colors to make this work. And so those are going to be what we call subtractive colors. And so this is where cyan, magenta, yellow come in. If you've ever had to replace your ink in your inkjet printer, they have those little cartridges, and some of them even have light cyan, light magenta, light yellow, something like that. But they never have red, green, and blue. They have cyan, magenta, and yellow. And if you've ever wondered why, I'm going to show you why it's those colors instead of the red, green, and blue that we would expect. It's because the printers are going to use the property of subtractive colors in order to get the colors of red, green, and blue, and so on that we are looking for. So here, if we take a look, here are our subtractive primary colors. So this is the magenta, the yellow, and the cyan. So these have been pulled apart so we can see what the individual prints look like with just those colors. Then down here, this is where they've been added together. So these three are laid over top of each other. Then just the black, and then the photo when they've all been laid together. So let's take a look at how these subtractive primary colors work, because to me this is like the coolest thing as far as how some pigments actually are working. Because I didn't understand for the longest time why I had to have these cyan and magenta cartridges. So let's take a look in the picture over here at the red balloon. Okay, so the red balloon right here, and cyan is going to absorb red. It's going to absorb red light. So let's take a look at that balloon on the cyan print. It's right here by the kid's head. And if you notice, there's really no cyan on that part of the print. And that makes sense, because if we want the red to show up, we don't want the cyan there because it would actually cancel it out. And if you look at that red balloon on the yellow and on the magenta, those two together are going to work to add together to make that red color. If we do the same sort of thing for like a green balloon, so magenta is the opposite color of green. If we think back to our opposites for the primary colors, so if we take a look at where the green balloon is on the magenta print, there is the green balloon, and sure enough, it's white basically. There's no magenta printed on it. And if we look at the yellow and the cyan print, they do have color in those places in order to work to make the green color. We'll check one more that's easy to check. Blue, so we've got the blue balloon here, and the opposite of blue is yellow. And look there, that balloon is completely empty on the yellow sheet. And you've got cyan and magenta both coloring in for that balloon to add together to be able to show blue. If you look at this picture right here on D, it actually looks okay. It's not great, but it's okay as far as the colors. They're all there. The reason why we have the black, as you may be able to guess, is to sharpen the image, because we even do have some blacks in here, but they're not really great. And so we do the black print in order to sharpen all of the edges in that picture, because just trying to use those 3 pigments isn't enough to make great black. And so we're going to use a separate black cartridge just to make that sharp black show up. All right. So now we're going to move away from color and work on some more other properties related to light. The next one is refraction. So refraction is a little like reflection, but refraction occurs when you move from one medium to another with light. So for example, you can see here in the picture, we move from air to water. So reflection is when you bounce off of something. Refraction is when you bend into something. So it's the bending of a wave due to the change in the medium or the speed of the wave. So most often we're looking at changing in the medium, but for example, if you are in water and you hit a different temperature of water, that's going to change the speed of the light wave, because the change in temperature changes the kinetic energy of the molecules, and that changes how the light energy is going to run into those molecules. So to give you an idea of how this refraction kind of works, with a more real world example that you may have run into, I hope not, but see, so here we've got like a scooter, and you're going along in a straight line, and then you hit grass, right? This is like sidewalk, asphalt, something smooth. When you hit the grass, your wheels are going to jerk. And that is because, not that you've got like a curb or anything, but because suddenly one of your wheels is going to start going slower than the other. And so it's going to jerk and it's going to turn. And that's because when you move from that asphalt or concrete, you're going to be going from a faster speed to a slower speed. And so that slowdown turns your skateboard or scooter or whatever it is just a little bit as you move from concrete to grass. The same thing happens to light when it's moving along in air. And so it's moving along at its high speed in air, and then it hits the water, and now it slows down. And since it slows down, it turns a little bit. So what does this do? What can this create? One of the things that this creates is what we call mirages. So this is caused by refraction with hot air just above the sand. So this is one of those temperature refractions. So we're talking about air having different temperatures. So you have cooler air and then hot air right above sand or pavement. And so it bends the light, refracts it up and away, or well, down and away. It is refracting it up, but it makes things look like they appear below the individual. So you can see here, we've got a picture out on a hot highway. And so you can see what look like reflections of the motorcyclists and the car in the road. But they're not reflections, they're refractions. So the light has been bent so that it looks like they're in the road, but they're not actually in the road, as we know. This is also what makes things like water seem to appear out in the desert, because as you notice, it looks like a reflection. It looks watery, and it's because of this bend in the light due to that change in temperature. So the light hits that change in air and it bends and makes it look like it's going to reflect an object instead of just acting like regular light and going in a straight line. So how else does refraction work? So there are illusions that get created because of refraction. So for example, if you've ever been looking at like fish or something in a pond, or if you've been in a pool and try and bend over and pick up, you know, something that you've dropped, it's really hard to do that. And that's because the object looks like it's closer, not just to the surface, but also to you. And this is due to refraction. So when the light hits the water, it bends, and the object is actually farther away from you and deeper, but your eyes are still trying to see it in a straight line, just like with the virtual image. And so your object appears to be closer to the surface and to you. And that's why it's really hard to pick things up when you stay above the surface of the water. If you get below the water and look, now the refraction isn't happening anymore. The light rays are traveling in straight lines for you because they're in the water with you, and everything is okay. You can see here, this is a picture I took several years ago. And here, everything looks pretty okay with the penguins. I mean, this one is missing part of its body, and that's due to refraction. But the one that's really striking is the penguin over here, who looks like he's been chopped and scooted. So this is an example of that illusion of refraction, because the light is hitting the penguin, but it's being bent when it hits the water and makes the penguin's body look like it's scooted over. You can actually see this if you stick like a straw in a glass of water. You can see that it looks like the straw, has gone from being straight. When you put the water in, it looks like it's being separated. And so this is refraction that's going to be doing that to the objects. All right, I will actually start a new video on dispersion, because dispersion is fun and it's pretty, but it'll take me a little longer than what I want to add on to this video.